because my computer, none of them is working properly. That's why I'm using another computer these days. We have a set of correlation for heat transfer that we discussed that we can apply for laminar. We obtained this one in chapter 6. And then we have set another set of correlation. We mentioned that we have to make sure when we're applying to make sure that all these conditions are satisfied. And that will also be mentioned that this is the trend of heat transfer coefficient. As the flow becomes slowly laminar, the heat transfer value will slowly will drop. And then we have a transition part that is sort of mixing take place. Heat transfer coefficient will increase, and then when the turbulent again slowly will drop. Okay, that's exactly what happened.
Sir?
Yes, sir.
If the Reynolds number is above 10 to the 7, are we considering it too turbulent to be able to use that formula?
If you would like to, for this course, you can use this equation and you specify that yes, it is more than this, but however, I don't have any option because that's the only correlation I have.
Okay.
You're working for a company and you're responsible, then you have to go to the library because there is 10-book handbook of heat transfer and you have a variety of correlation, okay?
Okay.
This will just give you some example, one example, okay?
All right.
And then we mentioned that we take average, as we mentioned to take average, we take integral of the previous equation from 0 to L, and these are the value of heat transfer coefficient that they give you Nusselt number, the average from 0 to L, the average value, okay? And we mentioned for the case that we are not sure because as I mentioned, you have a 1 meter plate, and 1 meter plate, probably 40 centimeters laminar, 60 centimeter turbulent. Therefore, in order to take consideration of both physical phenomena, we can use the equation from 0 to x, sort of critical value, we consider laminar. From there, we can assume this one. Therefore, this equation, in case when we have a small plate, that the laminar component is as important as turbulent. But if you're dealing with something 10 meter, 20 meter, and you can see only the laminar portion is very small, we can go back and use this equation, okay? And then I believe we solved this problem. We did this problem, right? Last lecture.
Yes.
And then we went to end up with second phenomena that we mentioned. Now we are dealing with flow over a sort of cylinder or a sphere. As you can visualize here, you can see now the flow is passing through this one. Depend on the Reynolds number, the velocity that we have, we can come down, we call it creep, and then slowly go. As the velocity will increase, the momentum that the fluid has, it will jump here, will create some sort of turbulence in the backyard vortex component, okay? And in this case, we mentioned the critical term. Now the critical Reynolds number, we're talking about 200,000. And the characteristic length that we are going to use in order to calculate Reynolds number is the diameter of the pipe, okay? This is we covered last lecture. And we mentioned, again, depending how strong is jumping, we have different process take place. If you look at here, if you look at here, this is theta. And let me go back. The theta here this is equal 0, but it's perpendicular. This theta is equal 0. As we increase the theta value here from 0 to all the way to, let's say, 160, we can see the Nusselt number change. As Nusselt numbers change, it means heat transfer coefficient will change. As you can see, based on different Reynolds number we have, as the Reynolds number will increase, the Nusselt number will increase, and also heat transfer coefficient increase. Now, as we move in the direction here, we can see slowly heat transfer decrease. To go to the minimum here is around 80, 90 degree at this point, right here. And then will increase again because of this jumping phenomenon will increase because turbulence will increase and then go. Now, if you look at here, flow across a cylinder or a sphere in general involve flow separation, as we saw it in the previous picture. Here we're talking about, these are referring to local heat transfer coefficient. Look at theta. Theta represent as a function of this angle. Around the cylinder subject to flow, okay, as we mentioned here, if theta is small, okay, and this region decreases as increases theta result increase. Okay, this represent here, as you can see, the value that we have here. Theta decreases slowly, depending on the Reynolds number. And if theta between theta here, 80 and 90, this value right here, this theta in 90 is right here, this value here. You can see here the theta decreases slowly right here. This is the lowest value. And then as the theta increase, the value will increase dramatically. As here is 90 degree, as we link, the local heat transfer coefficient will increase, okay? If we can see here, the same thing that we had for plate. Now we have local heat transfer coefficient. The local heat transfer coefficient is represented by Nusselt number. Rather than showing a specific diameter, here they use dimensionless number to generalize the decoration. Therefore, this is the behavior of the local heat transfer coefficient we have, okay? From 0 all the way to 180 degrees, okay? But in most of the application that we're considering, we're not looking at the specific point. We look at here is what is the total heat transfer coefficient from this pipe or a sphere. Therefore, we are looking at average heat transfer coefficient. And to do that, we have a set of average heat transfer coefficient. This is the equation that we are using for a cylinder over a cylinder. If you have this equation that you can see, then this represents the average Nusselt number, and here's characteristic length again, the diameter, and you can calculate it based on this equation that you have, okay? For Prandtl number representing again characteristic of the fluid that you're dealing, this is Reynolds number and so on. That you can see it's a little bit sort of tricky equation that you have. Again, the reason because they obtained it experimentally and they find that this format represents the most accurate result. Again, this only applicable that the product of Reynolds number and Prandtl number is more than 0.2. Therefore, when you're using this equation, you have to make sure that satisfy this condition, okay? And then we are dealing with a sphere. Again, there's something I forgot to mention. All the physical property, when you're calculating Reynolds number, Prandtl number, again, we calculate at the film temperature. And the film temperature is the average of bulk temperature and surface temperature, okay? And when we're dealing with a sphere, okay, we can use this set of equation. And for a sphere, this was for cylinder, this is for a sphere. Again, you can see these are coefficient that you have it. Again, this is simply trying to take in consideration the effect of the temperature on the surface, because that temperature will affect also the viscosity. Therefore, this is also another part that they're trying to make this, we call it correction factor for different fluid, okay? And for these are a sample, again, my friend, please remember, this is a sample of equation just to show you that there are some correlation. If you're dealing with more sophisticated, does not satisfy this condition or more specific one, you can find in the library. Again, keep in mind, the two correlation are accurate. Remember, 30%. 30%. It means, again, this we have to be careful. These are our approximation of the heat transfer coefficient. If you're dealing with very specific, you have to go to the library, look at the handbook of heat transfer, probably find a much better correlation. You're talking about 30%. Again, the whole reason when they obtain this type of graph is based on curve fitting. They carry out the experiment on the sphere, on the cylinder, with different gases, with different diameter, and so on, with different air velocity, and then trying to fit in the curve, and they find this is the best curve for cylinder, and this is best curve for the sphere. Now, your textbook, they simplify again. You have a very nice sort of table. You don't have to write it down here. Look at here. This is table 7.1. This is table 7.1. And for different geometry, if you have a cylinder, circle, square, hexagon, and so on, and this is applied for the gases. Therefore, if you have the gas, liquid, this equation is only applied to the gas. This equation applied to the gas, but this one you can apply it to both fluid, liquid, and so on. And again, they specify when this equation can be applied. if you have a Reynolds number between 0.4 and 4, this equation you have to apply. Therefore, make sure that you're using the correct equation. Therefore, here, apply for the gas and liquid, and also you have to make sure that satisfy the range of the correlation that you have. For example, all of this are applying for the gas. Therefore, if you have a fluid, it means that cannot be applied because the Prandtl number does not match, and you have to go and find appropriate. Again, for each one, you can see there's a certain range. For example, for this hexagon, if it's in this range, you use this equation, and if it's in this range, you use this equation. Please, therefore, it's not just blindly take, I'm going to use the equation. No, we have to make sure that satisfy all the required condition. Again, it mentioned here that for most of them specify, as we mentioned, the Prandtl number is 1/3, but for the Reynolds number, depend on the top of, in the range of the Reynolds number that you have different value of n. Therefore, these are the value of the Reynolds number m. You have to make it, and these are the coefficient. Any question? Any question? Okay, it seems you are falling asleep again. Let me go to the next slide. And wake up. This problem I'm trying to solve. I would like to know how can I use it. Layer of 20 centimeter thick meat. We have meat 20 centimeter. Conductivity and thermal diffusivity is given. Initially is at the temperature of 7 degrees, and it will be frozen by refrigerator at -30 degrees. Therefore, initially at the time equals 0, it's 7 degrees. You would like to put it in the fridge. The temperature is -30 degrees. And at the velocity of 1.4 meter. I don't know what that means. The average heat transfer coefficient between the meat and air is 20 watt. Assume the size of the meat slab to be relatively large. I do not know why he's giving me that information. Determine how long it will take for the center meat temperature reach -18.
Sir?
Yes, sir.
So if they say assuming the size meat slab to be large relative to thickness, can we assume it's like a flat plate?
Yeah, that's good. That's,
Okay.
yeah, yes. You can assume it's a flat plate. That's
And the velocity, we're going to use it to get Reynolds number.
I have no idea myself. That's your problem.
Okay.
Please read the question very carefully. Find out what information has been given to you. What is the procedure? What technique? We have to use it. You have 2 minutes time, my friend. Any suggestion? Therefore, we have a slab, a mid. The thickness is 20 centimeter. Initially at 7 degrees. We place it in the fridge at minus 30 degrees. The air velocity is 1.4 meter per second. And the heat transfer coefficient is 20. How long it would take for the center temperature of the slab to be minus 18? Which technique should we use? Any suggestion? Come on, guys. 44 people over there. There is somebody can say and say something. Okay, let's start. The problem, can you tell me the problem to which chapter it belong? You have chapter 2, 3, 4, 5, 6, 7. Take one number. Yes, sir. Say it again.
Saying 4.
Oh, 4. Okay, good. Why 4? Why not 5?
I think because we have to calculate the Fourier number first.
Okay, because I do not know. He mentioned determine the time. I have to calculate the Fourier number, but how can I calculate the Fourier number, sir? Good. Very good.
I think first we have to check the bio number if it's more than 0.1 or.
Okay, good. Therefore, we are dealing with a transient problem. We are dealing with a transient problem. It's dealing with the time because the temperature changes as a function of the time. Therefore, we have to try to find out which belong to which category. Can I assume is it the internal resistance is negligible? It means the temperature everywhere is the same, or I cannot ignore that one. If I assume that the internal resistance to conduction is negligible, I can use the simplified equation. That's, you mentioned that if BO number less than 0.1. If the BO number is more than 0.1, it means there is a temperature distribution in the mid, okay? Therefore, the surface should be something, at the center should be something else, okay? Good, but then the first thing we should start to find out what is the BO number. Okay, let's look at here. Therefore, let's look at the restriction that we have. It mentioned the mid is very large. Therefore, as you remember, we have to 2L. 2L is equal 23. Therefore, the characteristic length that we are considering here is L. It means 23 divided by 2, okay? Because we assumed when you put in the fridge, both slides are at the same condition, okay? That's one of the assumptions we made when we're trying to solve this problem, develop the methodology. And then the second issue here is heat conduction in the mid is one-dimensional. Therefore, as you mentioned, because it mentions very large, therefore we can assume it's only one-dimensional. We are not should be worried about from two different sides, okay? The next here, the thermal property we assume is constant. Again, what we are saying here is we are dealing with the mid is 7 degrees, and then mid become minus 10 degrees. I assume the physical property both become the same. Again, this is an assumption that we are making, okay? The heat transfer coefficient is constant and uniform. Again, we assume the heat transfer is all over is the same. The average heat transfer remain the same, okay? Therefore, please, again, why I'm reminding here, when you're going to real life application, sometimes probably some of this assumption is not correct, okay? Therefore, you have to study how valid is those assumptions. And we go, as mentioned, we calculate, we go to that table at the end, and these are the information that we can find about the thermal conductivity and diffusivity. We assume mid is almost made of water, and these are the information that we can get, okay? Then, the first thing, as you mentioned here, is I want to know, is it the internal resistance? Internal resistance, it means when the heat reach the surface of the mid and then it start to diffuse through the mid by conduction. Is it negligible or not? Therefore, we calculate the BO number. And BO number, we mentioned this is the heat transfer coefficient. This is the thickness, L, characteristic length is L, 2L is 23, L is this one, and here the conductivity. And I believe this is more than 0.1. Am I correct?
Yes, sir.
Therefore, it is indicate we have a temperature distribution within the mid. The temperature at every point in the mid is different from the other point. Therefore, we cannot assume everybody is the same. Therefore, we cannot use the simplified equation. The simplified equation, it means the temperature everybody meet the same. But that tell us no, my friend. Now, where should I go now? Okay, give me some suggestion, my friend.
We have the other formulas that we can use that are not as easy as the bio number because we're not using the table.
Yeah, assume this is, you have to solve this problem. I told you now, you cannot use simplified equation. Now, tell me what is the next step? Come on, 43, you have to contribute to the discussion.
You can find the Fourier number and see if it's higher than 0.2. So
Okay.
you can use the.
Let me go back. Good point, sir. Good point. Let me go back. Let me see. This means how long? How long? It means the time. When I look at the Fourier number, it mentioned alpha t divided by L square. I do not know the time, sir. How can I calculate the Fourier number, sir?
You can use the graph.
I'm sorry.
Say it again.
I'm saying we need to use the equations. In this case, it's going to be for the wall.
Okay.
So we have one side from the temperature outside, and then both sides at the bottom, there's the initial.
Both sides are the same. We assume this is a mid, both sides are at the same condition. Both sides are the same condition. Now, if I remember it correctly, I have two options. The first option here is I can use the equation. Remember, if you have your textbook open, your textbook table, you have equation around table 4.2 that we have summation of 1 to n term, and then we have a simplified equation that we only consider the first term. Okay? Now, there is a condition again. The only time I can use that simplified equation if the Fourier number tau is more than 0.2. Am I correct?
Yes.
Okay. Therefore, now I have to make an assumption, or either can go use the figure, or I can use the equation. If I want to use the equation, I have to make an assumption that my Fourier number is more than 0.2. And then go calculate the time and come back and verify my assumption, okay? Please pay attention, please take it an initiative because we are getting close to the end of the term, okay? Therefore, table 2, we read from the plane, okay? This one, I go and use table 4.2 because I'm trying to use this one-term equation, simplified equation. And the simplified equation is this one, okay? This is the simplified equation that I have. Therefore, here is Fourier number is the only time I can use this equation if tau is more than 0.2. Now, in this equation, I have two unknown, A1 and lambda 1. These two numbers come from table 4.2. If you have not opened your textbook, please open it now, at least to see how that tables look like. You can see there's a column, give you the BO number, and based on BO number, you can read the lambda 1 and A1. Therefore, I made an assumption here again, that my Fourier number is more than 0.2, and I'm only using the first term here. And here, I know that my BO number, I can go table 4.2 and find out what is lambda 1 and A1. And I put it in the equation. Initially, it was 7 degrees. You put it in environment, it's minus 30 degrees, and I would like to see how long it would take to become minus 18. And from here, I can tell values right here. That's as easy as that one. Okay? Or you can go and use the figure. In the figure, you have this number, the y, and you have one BO number, and you can read the Fourier number at the bottom. Please, Joe, go open your textbook, and if you have any question, ask me. Therefore, you can use this one, and when you're using the figure, you don't need to make any assumption about Fourier number. But if you're using this set of equation, you made an assumption your tau is more than 0.2. And now we verified that value is correct. Please ask me if you have any questions.
Sir?
Yes, sir.
If tau was not more than 0.2,
Then you have to go and use either the big equation that you have summation of 1 to n, or you can use the figure.
okay.
Okay.
But using the value of tau that we get.
You get tau. Because if
Yes.
you remember, if you would like, I can show you the figure that I mentioned. The figure, your y-axis is this tau, this one, the temperature.
Yes.
And you have 1 over BO number. You have different line, and from there you can find your tau.
Yep.
You want to show it to you, or are you okay?
No, I'm okay. I remember.
How about the rest, 43? Any question? Okay, I'm just here. Therefore, you find that the number is okay. Therefore, your assumption that you made and you want to use this equation is correct. Okay, therefore, now you find is almost this one. From here, you have Fourier number, and Fourier number is alpha. You have alpha t time divided by L square, and then you calculate this value, okay? You find it's almost 22 hours, 0.1. Please read the problem one more time. And I have one question. Read the problem one more time, look at this solution, and let's go to the next part. This is from your textbook, problem 4.56. If you have your textbook, open your textbook. Here, we did it. Therefore, we started here. We assume it's more than 0.2. We use this equation for the first term. We went to table 4.2. We find alpha, lambda, and a. We substitute. We find the Fourier number. Well, it is 0.7, more than 0.2. Therefore, we are okay. Then we go back using the definition of the Fourier number here to find the time, and took 22 hours, 0.1 hour to get this one.
Sir, I have a question.
Yes, sir.
What if we get the Fourier's number smaller than 0.2?
Again, the question here is smaller 0.2. If you look at here, the figure that you have in your textbook is cover a wide range of Fourier number. Therefore, you can the second easiest solution. You can go and use the figure.
Okay, so if we get Fourier number smaller than 0.2, we go to the figures?
Yeah.
Okay.
Yeah, solution. Or you can use the other equation that you have, summation of from 1 to n. That I don't think so that you can solve that problem. Okay.
Okay.
But Any other question? Okay. Now, you're engineer, right? And this is engineering class, right? Yes or no? Yes? Okay. 22 hours. Do you think in reality
It goes faster than that.
is it faster or longer than that?
It should be faster,
Why?
because then the meat by that time may go bad, or the faster we get it to freeze, the better it is to conserve it. Like
Why?
conservation is better.
No,
I think it will be
Because
faster because of the air. We have
Oh.
air at just 1.4 meter per second. This air will affect the.
well, therefore, what is the influence of the air? Why I gave you the velocity?
The H is gonna change in your by it number.
Why we change it? The air velocity is given to you.
Chapter 7.
Chapter 7, good number, that's fine. Chapter 4, 6, or all of them have air velocity. But you know, if I come and give you the same problem in the exam, rather than give you this number, I give you the air velocity. What you do?
You calculate using you find H through chapter
Well, if I
7.
give you the air velocity, you can go back and calculate this one based on chapter 6 or chapter 7. Now let's go back to the question, engineers. I ask you, this number, how valid it is? Do you think in practice will be more than this or less than this? Remember, the meat is, we assume, is almost water, right? Then become frozen, right?
It will insulate the.
It becomes frozen, right?
Yeah, the ice will will make it longer because
Longer in what sense?
because it's a kind of insulation.
No, it's that needs. There is an energy need for the water to be frozen, right? It's become 7 degree, 0, and 0 stay, remember, until all the meat be frozen, and then from 0 go to -1, -2, -3. In this equation that we solve, we did not take in consideration the energy need for, we call it phase change, from liquid to solid, okay? Think about it, my friend. Think about it, okay? Let's go move later on. Again, we mentioned here, again, the second part, I'm sorry, I have to go back and forth. It mentioned determine how long it would take for the center of the meat of the slab to become here, the center. Therefore, the equation that we used, it gave you the center temperature. And also we mentioned determine the surface temperature of the meat slab at that time. Now, at the center, reach -18, the center of the meat, right? At 11 centimeter down there. We would like to look at that time, what is the temperature at the surface of the meat? Read the problem, think about it. Is it more than -18 or less than -15? And what do you think? I don't care about the equation, but first understand what is the question is asking you. The center of the meat is outside, is exposed to the environment. The temperature is -30. Therefore, you expect the temperature outside the meat at the center is -18. Therefore, the surface has to be much closer to -30, okay? Therefore, we go back. I'm sorry, this is a problem. We have to go back and forth now. Therefore, now we are calculating at the surface. If you remember, X or L is equal 1. At the surface is this one, okay? Now, if you look at that chapter 4, we have an equation also give you the temperature at any point. Not only at the temperature, because this was the equation that used for the center. This only gave you at the center. This 0 here, it gave you the temperature at the center, -18. We have another equation, is a little bit more expanded than this one, give you at any point, at x, at surface, at 16 centimeter, 14 centimeter, every point, okay? If you open your textbook and check the equation, and that's the equation that you have. The equation that you have give you the temperature at any point, and this becomes this plus this one. If you look at here, this equation is almost familiar. You already calculated this part. You already calculated this part. This part is equal T0 minus T infinity divided by T1 here. This is exactly this part. Okay? Now let me go back. Let me go back to show you. Look at here. A1E, this one, is equal temperature of the center. We already calculate. Temperature infinity, we know is minus 37 here. Therefore, this port, the first portion of the equation, we already calculate this part, okay? Therefore, rather than making difficult equation, you can simplify this equation and put this one, the one that we have here, okay? This one. T0 minus the infinity, okay? And X over L, you're trying to calculate. Therefore, you put this one equation and you calculate the temperature is become at the surface become minus 26.9, okay? Therefore, you have to have a judgment. If you do the calculation by mistake, you find the temperature is minus 17, it means you're wrong. The physics of the problem does not allow this one because the room temperature, the fridge temperature is minus 30. Therefore, the surface temperature, it has to be lower than at that center, okay? Any question? Any question? Therefore, this equation you can apply to calculate the temperature at any point from the center all the way to the surface. Is you change X over L, 0.5, 0.75, and so on, that you can find a profile of the temperature within the fluid. Do you have any question, please? No question?
I have a question.
Yes, sir.
If we want to find the time that it takes for the surface to reach this temperature, do we have to calculate another Fourier number, or we use the same number?
No, you already, we know the temperature at the center is minus 18. Here, look at here. It took 22 hours because if you look at this equation, I'm using this part here. Therefore, we already know at the time the temperature on the surface is minus 26. The temperature at the center is minus 18. And after 22 hours, 0.1, the temperature at the surface becomes minus 26.
Okay.
Remember, we use the time here to calculate. Here is exactly the time the temperature at the center reached minus 18.
Okay, thank you. I got it.
Sir?
Yes, sir.
But we don't have any reference of time in this formula here.
I do
We
have
only
it.
have
No, my friend. This is the equation. This is the equation. If you open your textbook, this equation. I use the A1, lambda 1.
or a
and
certain
tau.
value number.
That's right. This is tau. This Fourier number is for the 22 hours. This is the tau I used, is the same tau I use it here. The reason, my friend, look at the problem, read the problem. It mentioned determine the surface temperature of the meat at that time. Which time? The time the temperature at the center was minus 18. Therefore, when I try to calculate the temperature at the surface, I calculate after that time. Therefore, I used the same Fourier number that I calculate here. I use this one. Yeah. And this time is related to this time. This is my Fourier number belong to this time. Therefore, when I use the second equation here, the same lambda, the same A, and the same tau. This is the general equation. You can use this equation. You can put the same A1, the lambda 1 we got that, and the same tau, and put X over L equal 1. Therefore, we can calculate this equation, this part. Forget about this part, okay? If you use A1 that we used from table, lambda 1 from the table, and the tau we calculate for the case x over L is equal 1. It means x over L, it means at the surface.
Okay.
At x equals 0, give you the temperature at the center. Therefore, when is x equals 0, this becomes 1. Give you the temperature, okay?
So when you asked us what did we think about the time that it was taking to get to -18, you said that we should also take into account that we have a change of phase in the water.
No, my question was, in reality,
Yes.
you think the time will be more than 21 hours or less than 21? And why? That was my question.
Okay. But our number that we got was right.
No, the number was correct.
Oh, okay.
The number was correct based on this assumption.
Based on the assumption, yes. Okay.
Based on this assumption that I assume this remain constant.
So to be more correct, we should have gone to 0 and then check again our K and
No,
alpha.
to be more correct, this procedure will not apply at all.
Okay. All right. That way.
Because there is another physical phenomenon taking place that we did not consider.
Okay.
Because we have a slab of the meat, and there is a phase change because we are assuming the meat is 90% water. Therefore, we use the physical property of the water. In reality, if you assume it's water, not changing to the ice.
Yes.
Okay, it goes to 0 degree water at 0
Surface.
degree remain constant until all the water becomes frozen, and then goes from frozen water to -30. In this process, in between, this calculation does not consider. We call it phase change. Okay.
Okay.
No problem, sir. Therefore, here is that we calculated, and therefore, when the temperature at the 21 at the center become -18, at the surface become this. Please read the question. Do not know. Do you have time to write it down or so on? Because nobody talking to me. I assume everything is okay. Therefore, again, when we did this problem, we made an assumption that tau is more than 0.2, but we verified that was okay. But also phase change effect are not considered. And thus the actual cooling time will be much longer than this value, because there is a certain time we need energy to be transferred to change from the liquid to the solid. And based on this calculation, we assume, we forgot, we call this phase change. We did not consider this phenomenon. Again, just for your information, okay?
So it will be valid if we don't go to 0.
Yeah.
If we say 1 degree, it will be right.
That's okay. I assume here I treated this slab of the meat like a sort of a piece of solid material.
Yeah.
Not water. Okay. If I assume it's a solid material, let's say it's copper, that our procedure is correct.
Okay.
Now it was fluid. Now change it to the solid. There is a transition period. We call it phase change phenomena, and that we didn't consider. Just again, extra information I give you for general knowledge.
Okay.
Okay. Please, from the rest, 43 or 42 or 41, contribute every so often. Again, we assume for the property we'll use for fish and wet are the same. This we assume the conductivity of water is the same conductivity of ice. That's not correct. Okay, but this is an assumption. We have to make sure every solution that we have, it makes sense. Now, read this problem and try to do it. Okay. Therefore, it mentioned airflow parallel to a plate. Therefore, that represent could be chapter 6, could be chapter 7. The velocity of the air is given, 20 meters per second, and the temperature of the air is given, 250. Now we have two copper silicon bolts are embedded in the plate. The location of the first one is 25 centimeters from the beginning, and the second one is 1.75 meters from the beginning. Therefore, we have a plate, air going over surface, and at two locations, 25 centimeters and 175 centimeters from the edge. We have these two bolts. The maximum use temperature of this for copper silicon is 140. Therefore, this can take maximum 149 degrees, not more than that. Now we need to design a cooling system to keep the temperature of both maximum use the temperature, for we do not expect to be something more than that. It becomes necessary to determine the local heat flux to even give you the solution at the location where the bolt are mounted. Okay. Therefore, you have a plate. One point is 25 centimeters, and the other one is 175 meters. The air is passing over it by 20 meters per second, and the temperature of the air is 250. What we would like here is we would like to design a cooling system to provide a condition that the temperature at this point and at this point will not exceed 149. In order to design that cooling system, we have to know how much energy generated at that point. Therefore, at that point and this point, we would like to keep the temperature here. Therefore, what are the heat flux from the air at the location of this one? I have to know how much energy has been transferred from the air to this bolt. Then I design a cooling system that to compensate for that heat. What is the procedure, ladies and gentlemen? I believe what I have to do next time, I have to ask all of you to put your camera on. At least I can see who is sleeping, who is working. Okay, any suggestion? What should we do? In order, therefore, it's representing the heat transfer from the solid to the air, or from the air to the solid. Therefore, I have to apply the Newton cooling law. The Newton cooling law, it mentioned Q is equal HA, in case H times delta T. I know the delta T, the air is 250 degrees, and the temperature of the surface, I do not want to exceed 149. Therefore, I can say maximum 149. Now I need to heat flux, therefore I need to calculate the H. Therefore, my heat transfer coefficient, but I need it at a specific point, Therefore, I need to calculate my Hx at this point. Okay, I have to calculate my Hx at this point. For example, for the first case, when I calculate my Hx, H at 0.25, I know the delta T, therefore I can calculate the heat flux. Q equal H times delta T. Delta T is known, the only thing we calculate. Now, I have to calculate my H, heat transfer coefficient, a local one at this point. Therefore, the first thing I have to do, I have to calculate my Reynolds number. Because I have to calculate Reynolds number to find out if it's laminar or turbulent. In order to calculate my Reynolds number, I need to calculate the physical property. Therefore, I have to go back, again, we are dealing with the air. This is the case that we have. Air is coming here with a certain velocity mentioned. And this is the first bolt, and this is the second one. Location here from the edge here, here is 25 centimeter. The second one is 175 centimeter. We know the air is 250, and the bolt here is assumed is 140. Okay, therefore the first thing here is you have to make an assumption. The first assumption I make here is the air is passing here. When it reach this plate, will not be disturbed. That's it. Still, I can assume this is my bulk velocity. Okay. Therefore, the flow is steady, incompressible, uniform temperature, and therefore this is uniform temperature surface. Everywhere is assuming the same temperature, and the flow is steady and incompressible. It means we can assume that air density and so on is independent of the temperature and everything. Then I go back, dealing with the air. We're dealing with the air. We go to look at the physical property, and there's a table at the end, and the table is A15. Remember this magic number, A15. And again, in this case, the temperature here is 149, the temperature is 250. Therefore, the temperature change from here to here, the physical property change. Therefore, we take the average temperature. This is called the film temperature. Film temperature is the average of the surface temperature and bulk temperature. And that's therefore we have to look at the physical property of the air at 200 degrees. Let's go and look at A15, the end of textbook, to see what is the conductivity, what is Prandtl number, and what else we needed. Kinematic viscosity. Please use a table, table A15, to look at these physical properties. Okay. If I'm making mistake, this is the value. Or if I'm not making mistake, Prandtl number is almost 0.7. We're dealing with air, conductivity is this number. This is kinematic viscosity. It means viscosity divided by density, okay? These are the numbers that we have. Continue. I'll give you another 2 minutes.
But sir, for the calculation of the Nusselt number, you use the conduction of the bolt, or?
No, sir. In Nusselt number, the conductivity is the conductivity of the air.
Oh, yeah, okay.
Right? Very good, sir. Therefore, first we calculate the Reynolds number. In order to do that, as you know that we have two equations, one for laminar, one for turbulent. And we do not know, for example, 25 centimeter, if it's, and that location is laminar or turbulent. Therefore, we have to calculate Reynolds number to find out where is this transition happen, okay? Therefore, we do the calculation. And we find the critical length. The critical length is this one. Therefore, at 80 centimeter, 86 centimeter, flow goes from laminar to turbulent. Whatever is before that is laminar. Therefore, for 25 centimeter, we know that the flow is a laminar. Therefore, this equation that we have, Reynolds number, this is the critical number. And critical number, it means at 500,000, it changed from laminar to turbulent. Therefore, I find where, now I go back, where the flow goes from laminar to turbulent. Here is 25 centimeter. Therefore, somewhere from here, the flow becomes turbulent, okay? Therefore, this part is laminar part. Therefore, I can use for this one, the equation, the local Nusselt number, assuming it's laminar. It means 0.332, Reynolds number 2.5, and so on, okay? Therefore, here we go back, and we use this one. And therefore, we calculate the location here is laminar. And I will use the laminar here. I can find out my Reynolds number at 0.25 because I'm calculating the local Nusselt number because they ask us the local value. Therefore, the velocity, we know that. We know at which point I want to calculate. And here is my kinematic viscosity. Therefore, now I have the local Reynolds number. I know is laminar. I go and use the equation that I have Nusselt number x is equal 0.332, Reynolds number 2.5, Prandtl number 2.1/3, okay? Therefore, knowing this is laminar, I can go and use that equation that I have here. This again, I change it directly to calculate the h. This times is divided by Nusselt number, 0.332. This is Reynolds number that at 25 centimeter. And the Prandtl number is irrelevant of the location, it's characteristic of the air, therefore we can calculate here. Therefore at h at 25 centimeter, at that specific point, okay? At that specific point, this is very important to remember that a specific point, the heat transfer is this one. If 20 centimeters is different, 30 centimeters is different. But this is we call it the local, at 0.25 centimeter, the heat transfer coefficient is that value. And he asks us how much energy has to be removed from that specific point. That's why I have Hx at that specific point, and I know the temperature difference. Temperature heat difference is the temperature of the plate, 149 maximum. Temperature of the air, T infinity. T bulk is 250 degrees. Therefore, based on that one, I can calculate the value of the heat transfer. What happened to my, okay, here, local Nusselt number. And here, we go back and calculate the heat transfer. This we calculate already. This is the temperature of the air is coming here, 250. And according to STM, the temperature should not exceed 149. This will be the maximum. Therefore, this amount of the heat has been transferred. Any question, please? Have you been able to finish writing? Do we need more time?
Just one more minute.
No problem, sir. Okay.
Can you go to the previous slide, please?
Say it again, please.
Can you please go to the previous slide?
This one here, sir?
Yes, please. Thank you.
No problem.
Once it's done, if you can go back after when he had finished writing it, if you can go back to the whole problem, because I think I misread 1, 2 thing.
Okay. Done. Okay, let's go back to the problems here. Yes, there. This is from textbook. I believe I gave you the number for the, let me see, did I give you a number or not?
No,
I believe it's 635. Check your textbook. This come from your textbook, 635 or 36. I forgot to put the number. I'm sorry. It's coming from your textbook, okay?
Okay, thank you.
No problem. Now, we calculated for the first place, 25 centimeter. Now, at the second point, what do you suggest now? What should I do now?
We have to use a turbulent.
Excellent. Therefore, we calculated at 80 centimeter. After that, become turbulent. Therefore, we don't need to go back. Therefore, we go back and immediately calculate the Reynolds number, and we place it in the equation that we have for here. At this point is bigger than this point, therefore it's laminar at the turbulent. Therefore, we go back. Again, we calculate the Reynolds number for that specific point, 1.75. And then, since it is turbulent, we use the equation that we have for turbulent flow. Again, look at here, we're calculating local value. Therefore, here we calculate 25, this one. When Reynolds number is more than 500,000, that shows it's turbulent. And then we go look at the equation that we have for turbulent, the local heat transfer. Again, the local heat transfer that we have, and we place it there. It's a constant times Reynolds number 2.8, Prandtl number 1/3, okay? Again, please write those equations that you need. You can bring 2 pages of equation, 2 page back and forth, it means a total of 4. And if it's a table, equations given the table like 7.1, I will provide you, okay? Therefore, here we have this equation now. Look at here. This is 0.8 for turbulent flow. The Prandtl number is the same. This coefficient is changing, okay? And based on that one, we find out that the heat transfer coefficient is 36.14. Again, the problem is asking you how much cooling we have to provide that at the specific point. How much cooling we have to put at the specific point. Therefore, we have the heat transfer coefficient. We know the temperature difference, 250, 149, and we can calculate the value of this one. Okay? Please read the problem, understand it, what is given to you, what assumption that you make, because the assumption that you make that will help you in your future. In the future, you have to make a judgment that should I use this or not, because it's not memorization. You have to understand the physics of the problem that be able to make a judgment, what exactly I have to do, okay? Any question? I cannot.
Can you hear me now?
Yes, sir.
Okay. If we need the average H, how do we go about? Do we use the Nusselt number, the average, like the laminar and the turbulent, or we
Yes,
separate
yes.
them?
If they ask you what is the total energy from that surface, therefore you take the average value. The average value is still, you calculate your Reynolds number based on this length, because the question here, what is the total length? And then you use the equation that given to you. That's correct, sir.
But do we separate them? Because there is Nusselt number for laminar and for turbulent,
But
right? And for the turbulent, there's like a,
yes, yes,
it includes laminar also.
But if you're trying to calculate the average heat transfer, you can use the last equation that you give it to you, because that last equation considers the contribution of the turbulent and laminar. Okay, look at here. The pay here is after 80 centimeter become turbulent. Therefore, it means the first 80 centimeter, is laminar. The next one is turbulent. Therefore, both of them have probably equal contribution. In that case, if I was going to use it, I would use the last equation that has consider the laminar contribution plus the turbulent contribution.
Okay, perfect. So if another plate, which let's say the turbulence starts from the beginning, then this last equation will be wrong, right? We have to use the second.
The last equation is not wrong. The last equation considered the exact phenomena. There is a laminar and turbulent. But if you look at, for example, in this case, that you have 175 centimeter, if the first 20 centimeter was laminar, if you were using this equation, and they give you the critical number if it was 20 centimeter. Now you have 175 centimeter, the first 25 centimeter is laminar, and 155 is turbulent. Therefore, if you use the second equation, that for turbulent is also correct. okay? But you can use the third one is absolutely correct. Did I answer your question, sir?
Yes, thank you.
Okay, then let me go first, okay? Just let me go back again. I'm sorry with all this back and forth. I use so far, I lost 2 keyboard because always I have to go back and forth. My keyboard does not take anymore any joke. If you look at here, when we develop this equation here, we assume this is a one tube here. For example, inside is you have a fluid and outside the coming air, or inside is one fluid, outside another. Therefore, we assume here the air is coming here is undisturbed. Air velocity everywhere is the same, and come and interact with this tube, and then depend on the velocity, separation occur, and there is something. But assume now that you have 2 tubes, and the second tube is here, right here. What will happen? What will happen here is the velocity of the fluid coming to here is not anymore uniform. Therefore, this pipe will affect the velocity profile and therefore the heat transfer profile. And that's exactly happened when we're dealing with heat with the heat exchanger, okay? When we're dealing with heat exchanger, this is exactly happening here. We're dealing with like this, we have a number of the tube here, we call bank of tube, okay? And therefore there are in parallel here, probably you have 5, 6 row, 10 row, and this direction have another number of the row, okay? Therefore, when air passes through this pipe, the velocity profile of the fluid will change, and when you pass the second one, change. Therefore, by the time to get to the last one here, the velocity absolutely different. Velocity profile is absolutely different than the one reached here, okay? Therefore, here we also have to do the same thing. We are not interested only look at the performance of one tube. We are trying to look at the performance of the heat exchanger. Therefore, we're trying to come up with a sort of a technique to calculate the average heat transfer coefficient. Therefore, we call it cross-flow over tube banks. Here called banks of the tube, commonly encountered in practice heat transfer equipment like a heat exchanger. In such equipment, one fluid moves through the pipe, inside the pipe. One fluid, this could be water, it could be any fluid, and another one is over the pipe, okay? Therefore, we are dealing with 2 types of fluid, one inside and one outside. Flow through the tube can be analyzed by considering through flow is simple. Therefore, here we know the solution already. You have to take in fluid mechanic, the fluid passing here, you can calculate the pressure drop, you can calculate everything. But for the over tube, the velocity pattern will change. The fluid velocity outside change from one tube to the second tube and third tube and so on. Therefore, we are trying to come up with a technique to calculate the, again, heat transfer coefficient. But at the end, my responsibility, your responsibility here is to design this heat exchanger. To design heat exchanger, you have to understand how much energy has been transferred from this fluid, red one, to the tube, okay? That's one technique you have to do. Okay, therefore, what you need to do, you have to calculate the heat transfer coefficient, because here is solid pipe and fluid. Heat transfer is by convection. By convection, what I need to calculate the H, okay? That's one we're trying to do. Let me see how much time we have. A few minutes left, okay? Therefore, that's one of the things we have to do. Usually, there are 2 different type of design, okay, the heat exchanger. One, we call it inline. Look at here, there is a spacing, there are a space from each other nicely in this direction. But we have also staggered here. Look at here, there are one between these 2 pipes and so on, so on. Therefore, we are dealing with 2 type of design. We call inline and staggered. These 2 techniques. Okay, therefore, whenever the same thing, we have to make sure when we are using the heat transfer coefficient, we have to know it has been, is it such a design or such a design? Because absolutely the flow pattern is completely different, okay? Therefore, this is, we have to keep in mind what they, and the characteristic length, again, we are using in calculation of Reynolds number and so on is D. This is the characteristic length, okay? We are not dealing with the length because flow is going over the pipe. flow going over the pipe. Therefore, the characteristic length here is. And again, we have to pay attention to their design. The design here is the distance in this direction, okay? As design in this direction, okay? The distance here, we call it SL, and the other one here, we call it ST, okay? Transverse pitch and longitude pitch. Longitude, transverse, okay? And when we're dealing also with the case of target, we need also another dimension between these two, okay? You have to, okay? Now will I stop here? I will stop here and we will continue next lecture. Please read chapter 2, 3, 4, 5, 6, 7. I will again next lecture, we are going to finish chapter 7, but before that we do want some problem from other chapter to help you to remember again, okay? Again, please, we have to start to work hard. Any question? Any question?
Sir, could you remind me what's edge effect again?
Pardon me?
Edge effect. What's edge effect? When we make assumptions, we assume we neglect the edge effect.
Edge effect, okay. Edge effect here, look at here in this case. For example, in this case, the plate starts from here, right?
Yes.
And assume you design and we place the fan here, right? Okay, you're trying to provide cooling it down, okay? Now the air comes here, so far we assume is almost a uniform air velocity, okay? And then comes the approach here, air becomes disturbed. But here we're assuming still the velocity is uniform.
Okay, so that's edge effect?
Yeah.
Okay, perfect, thank you.
What else? Okay, thank you very much. I'm here. If you have any question, I will stay here. If you have any question, please feel free ask me. And if you have any question, anything about your program, project, let me know.
Just by curiosity, for the midterm, even if it's like in a while, you sent us the like the procedure, but I was just wondering, is it just one answer, or we have to write, actually we use this formula, write it down, and will we be able to write down on a paper our stuff? Because I'm just figuring out like how to prepare myself for that, because if we cannot write down anything during the exam and just be on the computer, it's a whole different challenge.
I believe you have to write also your solution, and again they are going to be in contact with you, tell you, probably they will ask you to take a copy with a picture and upload it.
Oh, okay, so
the procedure is important because I'm not only answering 25 or 26 now.
No, I totally understand. Yeah, it's just that it was more about like the setup of the camera and like,
because again,
like the procedure for the cold thing, but
yeah.
Then the rest, I know the different teacher asked for different things, so I was just wondering.
In my case, again, probably you're much more familiar with the technique. Probably some of you have taken some courses during summer.
I took, honestly, Mr. I took like since last winter, I had 10 class, and honestly, I had probably 8 different methods for testing and quiz and exam and submission. So
excellent.
It's really not uniform.
This is good. No, you become an expert.
I hope, but are you an expert?
I'm not expert. As an expert in examining, therefore there is a lot of opportunity these days. Nobody knows how long this mess will continue, but I'm joking anyway. But again, we will provide you. I'm trying to, again, my request, I told them I need to be done on the system, and I asked them I need to have the solution, but probably I do not know again the setup. Believe me, I have no idea. Probably they will tell you upload your result, and that's based on that result. Also, they give you probably some time to upload, make a copy and upload it.
Okay. Okay. So yeah, as soon as you know, I guess.
Sure.
Let us know. Thank you.
No problem. Any other question? Anyway, if you have any question, I will be around here. Shout, scream, I will answer you.
Thank you, sir.
Thank you. Thank you again.